We often find seemingly impossible proofs that show that 1 equals 2 or 5 equals 4. But what are these mathematical fallacies and what is the importance of them? A mathematical fallacy is an assumption or a series of steps which are seemingly correct but actually contain a flawed argument, usually hidden deceptively. Mathematical fallacies are used to bring attention to these flawed arguments and highlight the dangers of ignoring certain rules. For example, the division by zero fallacy starts with a equal to b. If we multiply a to both sides and add a squared, it will result in 2a squared equal to a squared plus ab. From there, we would subtract 2ab from both sides, where we would get a squared minus ab on the right side. Then we can factor out a 2 and a 1 and then cancel the expression in the parentheses, resulting in 2 equal to 1. Can you tell where the mistake is? The mistake can be found in the last few steps of the proof, where we would be dividing both sides by a squared minus ab. This results in 2 times 1 equal to 1 times 1. However, since we said at the beginning that a equals b, a squared minus ab equals 0, this expression would equal 0 divided by 0, which does not equal 1. 0 divided by 0 is what we call undefined, and is the flawed argument in this division by 0 fallacy. Another example of a mathematical fallacy is the square roots proof. If we start out with negative 20 equal to negative 20, we can split both of these numbers into different expressions. From there, we can manipulate these expressions into completing the square, resulting in 5 minus 9 halves squared equals 4 minus 9 halves squared. Then we can take the square root of both sides to get 5 minus 9 halves equal to 4 minus 9 halves. If we add 9 halves to both sides, we get 5 equals 4. As suggested by the title, the mistake can be found right when we take the square root of both sides. When the square root is taken, there is both a positive and negative solution, resulting in two answers. When we take the negative solution of the left and the positive solution of the right, we get negative 5 equal to negative 5, which is correct. The answer we came up with is when you take the same side, either both positive or both negative on both sides. This results in what is called an extraneous solution, which is a solution that is not valid to the problem. This mathematical fallacy is called the complex numbers proof. It starts with negative 1 divided by 1 is equal to 1 divided by negative 1. Then the square root is taken and is split between the numerators and the denominators. A complex number can be defined as I squared equal to negative 1, so we can rewrite this equation to equal I divided by 1 is equal to 1 divided by I. Next, we multiply 1/2 to both sides and add 3 over 2i. Then we multiply I to both sides, resulting in I squared divided by 2 plus 3i divided by 2i is equal to I divided by 2i plus 3i divided by 2i. Since I squared is equal to negative 1, we can simplify this back and get 1/2 plus 3/2 is negative 1/2 plus 3/2 is equal to 1/2 plus 3/2. If we multiply 2 to both sides of the equations, we get 1 is equal to 2. The mistake in this problem was actually way earlier in the process, where when taking the square root of a fraction or two numbers multiplied together, you can only split up the square root if the values a and b are non-negative numbers. In that step, we try to split up negative 1 divided by 1 and 1 divided by negative 1, which cannot be done. This is a geometric mathematical fallacy trying to prove that all triangles are isosceles. There's also a similar fallacy proving that all triangles are equilateral, however, they go over very similar steps. We start off by saying if the angle bisector of A and the perpendicular bisector of BC are parallel, then ABC is isosceles. If not, then they meet at a point P. The perpendicular line can be drawn from P to a point on AB, creating EP. The same can be done for FP. By angle side, the triangles AEP and AFP are congruent, and therefore EP equals FP. Since D is the midpoint of BC and share PD as a side, then PB also equals PC. With these facts, we can conclude that BE plus EA is equal to CF plus FA. Therefore, ABC is isosceles, right? The accurate representation of the triangle shown in the following picture where the same lines are equivalent. AE still equals AF, EP P still equals FP, PB still equals PC, but AB cannot equal AC. This is due to the fact that BE plus EA does not equal AB, while CF plus FA does still equal AC. The original proof did not account for EP to form outside of AB, and this proof illustrates the importance of betweenness and how one must account for the order of points. The last mathematical fallacy is integration by parts proof, which is a calculus proof. The formula for integrating by parts is shown above, taking the integral of u dv is equal to uv minus the integral of v du. For example, if we take the integral of 1 over x dx using integration by parts, we can find the values for u, v, du, and dv, where dv equals dx, v equals x, u equals 1 over x, and du equals negative 1 over x squared dx. Then we can place these into the formula, and after simplifying we end up with the integral of 1 over x dx is equal to 1 plus the integral of 1 over x dx. Then we can cancel the integral of 1 over x dx on both sides, resulting in 0 equaling to 1. The issue comes from canceling out the integral. There's a crucial value left over if you do subtract these integrals, where little c is equal to 1 plus big C. These c's are what we call the constants of integration and are crucial to indefinite integrals. Another way to catch this mistake is by making these definite integrals instead, where we'd end up with the integral from a to b. The integral of 1x dx from a to b is equal to 1 minus 1 plus the integral of 1x dx from a to b, where 1 minus 1 would equate to 0 and the equation would remain true. In conclusion, mathematical fallacies teach valuable lessons, as are shown by the various examples we've gone over: the division by zero, square roots with extraneous solutions, complex numbers, isosceles triangles illustrating the importance of betweenness, and integration of parts with constants of integration. So next time you want to impress or stump your friends, show them a mathematical fallacy and see if they can figure out the mistake.